So to review, brittle deformation. Two basic types of brittle deformation happen. Tensile cracking, which can be from tension or from compression. So as it's kind of like if you have an envelope and you squeeze the top and the bottom, it kind of bulges in the middle. That's a tension crack caused by compression. You could get the same effect if you could grab the sides and just pull them, like when you're opening a bag of chips or something. And these cracks propagate from Griffith cracks. I'm sure everybody remembers Griffith cracks are those super tiny cracks you can't see, but they are all through the rock and they weaken it, and cracks usually grow from those. They can be imperfections in the grains, imperfections in the crystals, or just simply it's where the two grains are touching each other is weaker than inside one of the grains. Shear fractures are ruptures that happen that break the piece of rock or the body of rock into two distinct pieces, and there's some kind of shearing motion to it. Large example, San Andreas Fault. Small example, you step on a piece of ice and it breaks, and like you step on an ice cube and it breaks into a bunch of pieces. So what happens when this is going on? A tensile crack forms due to a load, i.e. a stress, applied to the rock, and it changes the energy of the system. If you think about, you're exerting force, so you're applying pressure, therefore energy, and it's changing what's going on. It builds up stress until something happens. Either it moves, it breaks, it deforms, something to relieve that stress. The three parts of the energy system, you're not going to have to do this in the lab. This is to explain it. So don't freak out over this part. But you can break the energy into three different categories. There's sum of energy, that's the actual load that you're applying. You're either pushing on it or you've set something heavy on it or whatever. There's the stored strain. So it's like if you have a spring and you compress it, there's energy stored there. As soon as you let go, it'll expand. Rock, if it compresses, has stored strain. We talked about the elastic moduli and how then the rock tries to return to its original shape. Also, if you're stretching a rubber band, you're stretching it, there's stored up energy. Somebody comes up and cuts it in the middle, you'll feel that energy very sharply in your fingers. And then there's the surface energy along the crack itself. You can set up equations that show the different parts of the energy and the load applied. And if it's at equilibrium, there's no change. Therefore, it's just shifting where the energy is. The energy goes from your applied load into something else when it breaks. Specifically, it releases all that energy into the energy of the crack surface. So if the cracks don't get big enough, they don't release all of the stress you've applied. That's why, like shear cracks, go all the way through. They relieve all the stress. That is important when we look at the size of the Mohr circles and what happens when the rock breaks. Now, Mr. Griffith had cracks named after him, so he felt special. But more importantly, he figured out why or when the rock is going to crack. That's why they named him after him. This equation here is the minimum stress needed to break something. So sigma t is the minimum tensile stress, either literally adding tension or tension caused by the compression in the perpendicular direction. E is Young's modulus that you've seen before in the semester. Gamma is the energy that's going into the crack. So that's why I said, when you apply the stress and the rock breaks, the energy moves from your stress to the actual cracking action and breaking the bonds and so forth. And lowercase c is the half length. Nice straightforward name. It's literally however long the crack is, divide that by 2, and that's your half length, using metric system, of course. Because half length is in the denominator, if the crack is bigger, it takes less energy because your number gets smaller. It's like if you have a piece of paper, and you're pulling on it, it's pretty hard to just pull it straight in half. You get a little bit of a crack in there, it didn't take much force at all. It ripped. If I had started with a bigger crack, I would have barely had to do anything. So the longer the cracks are that exist, the less and less energy it takes to break the rock. Some other folks came along and said that basically it's a little bit too hard to measure all of that stuff. Let's use experimentation and figure out something called the fracture toughness for a given material and rearrange the equation to use that. And so you can look up fracture toughness or fracture, basically strength of a material in charts and tables and stuff, and use this equation to figure out, hey, is my stuff going to break under this stress? The only thing that they had to add in there is the orientation of the cracks. For example, I was pulling sideways on the paper, and the crack was vertical, so it let me rip it easily. If I take another piece of paper and I have a rip going the other way, it doesn't help me tear the paper. So the orientation of the cracks really matters. Shear fracture criteria and shear failure criteria are just two words for the same thing, so sometimes you'll see one or the other, even in your textbook. And what it's getting at is what it takes to break the rock into two pieces. So it shears all the way through. And this only happens, you're only going to get shear failure if all the stresses are compressive. So if you actually have tension in at least one direction, it's not a shear failure. It's purely tension cracking. So this equation we'll actually use today. This is the equation for shear failure, and this is what goes into the Coulomb failure envelopes that I know the engineers have heard of, because some of you guys are asking me about them. So sigma S is the shear stress. Capital C, this time is different than the other C, is the cohesion of the rock. Basically, how good does this rock stick together? Mu is the coefficient of internal friction. So how easily does the rock slide? If you have loose sediment, it has a very limited internal cohesion. It slides pretty easily. If you have a well-cemented rock, it has a very high coefficient of cohesion. If you have a crystalline igneous rock, it may or may not have a high internal cohesion, depending how well the crystals are interlocking. Sometimes a rock will fracture very easily between the crystals, sometimes it doesn't. And then sigma n is the normal stress. Hopefully I don't have to say this, but just as a reminder, normal here doesn't mean that it's like common. Normal is perpendicular. So whenever I'm using normal, it's the perpendicular stress. So, cool equation. What does it mean? Why do you care? Well, the more normal stress there is, the harder it is to move it, the more shear stress it requires. It's like if, I don't have a textbook here, but I'll use this bucket. If it's just sitting here, the only normal stress is its own weight. I can push it along pretty easily. If somebody came and stood on this or set a 50-kilogram weight on it, it would be really hard to push it. It would take a lot more shear stress to get it to slide. More internal friction makes it harder to shear or slide. It's like the difference between if I have this sitting on the desk or a piece of glass, or if I set it on a piece of rubber that's really grippy with lots of friction. Higher friction makes it harder to slide. And then more cohesion. Again, the more cohesion, the harder it is to slide. You know, it's like if I glue that down, there's lots of cohesion. It's not going to slide very well. So the higher the rock's internal cohesion, the higher the rock's internal friction, and the more normal stress there is, the harder it is to shear. And this is where we can use more circles. Yay! On a Moore diagram for stress, different than our Moore diagrams for strain that we used last week. Different axes labels and different angles that we draw on our circles. But other than that, you know, they're still circles on an axis. So now we can plot a line called the Coulomb failure envelope that is an equation sigma s, the shear stress, equals C, the cohesion, plus normal stress, and then tangent theta. Now, this theta we don't necessarily have initially. So yes, that's the equation of it. Theta there is the angle that the rock will break if you crush it until it shears. So since we don't have that yet, if we're predicting the rock breaking, oops, I guess I don't have it in the slide. It's in the lab. We'll use mu, which is a term for the internal cohesion values for the rock. And I give you some mu's in the lab. And then you'll end up plotting the Coulomb failure envelope, and you'll end up finding theta instead of being given theta. Now, stress circles can never cross that failure envelope, ever. Not even briefly. As soon as the stress is such that the circle touches that line, the rock breaks. Transfers some of that stress energy into cracking, and the circle shrinks. So every time it touches that line, the rock breaks and the circle shrinks. That's why it'll never go across that line. Now, Otto Moore, that these are all named for, refined that envelope. He said, okay, the straight line is good, but it's not perfect at very low and very high confining pressures. He did experimentation and figured out the ends of the line should curve. So a lot of times you'll see failure envelopes that curve near the y-axis and then far out curve as well. But the straight line is a nice approximation and a lot easier to graph than finding one of these curves. So at least for lab and for a lot of work that you'll see, it has a straight failure envelope. So what it means is this rock is fine. It's safe, it's happy, it's not going to break unless something new happens to it. This rock is captured in the split, nanosecond in time when the crack starts happening. It's in the process of breaking. And so in real life, you'll never actually measure a rock that's like this, because as soon as it's here, it's breaking. And then this is completely and utterly impossible, never going to happen. The rock broke before the circle could ever get that big. So sliding on a fracture plane, what's actually going on? We know friction plays a big factor in it, and I know she covered a little bit of this in lecture, but want to refresh it. we know the basic definition. Friction is resistance to sliding. But why? What causes it? What's going on? Basically, there is no surface on Earth that is smooth. Even the thin sections that get sent off and polished super nice, or glass that's polished up for mirrors and stuff, isn't truly smooth. Every surface is jagged. The little bumps on it are called asperities. I think you've seen this picture at least in the textbook, if not in lecture. And so those little bumps and jagged edges are cutting into each other. And you try and slide it, and they bump each other, they cut into each other, they break. It's absorbing energy. If you push down on it, exerting normal stress, they dig in even more and more. That's why adding weight on it makes it harder to slide. Force that's perpendicular to it. Yeah, I just said that. So it turns out, though, that the amount of the force is important, but not the actual surface area. So you figure if you spread the same force out over a large area, the little jagged edges don't dig in very much because it's spread out so well. If it's over a narrow area, they dig in really tightly, and it ends up being the exact same amount of friction. So stress is going to change. Stress is force per area. But the force is the important part. An example, if you have a nice big 4x8 sheet of plywood, stand it up on its end and drag it across the floor, or lay it down flat and drag it across the floor, it takes exactly the same amount of force. Because it's the same weight. It's the same piece of wood. They've done tons and tons of experiments with this over centuries because it seems really counterintuitive. You think, well, the less of it that's touching, the less friction there will be. It's not true if the force, the weight, stays the same. So why am I going on and on about friction? When a rock fractures and there's stress on the rock, we want to know, is it going to slide along that fracture plane? Or is the friction too much? Is it going to be just a joint, or is it going to be a fault? Will it create a new fracture to slide along instead? So if it's also important to know that if something isn't moving yet, the friction is greater. We call it static friction than if it's already moving. It's like who's tried moving furniture and you have to push really hard until it gets going and then it's easy? Yep. While it's stationary, there's more friction. You think about it, the asperities are really dug in. Once you get it moving, they're sliding past and braking, and there's momentum, and it makes it easier to keep going. This applies to fault blocks as well. Getting a fault to start moving takes a lot more stress than getting it to move a bit more once it starts. That's why they worry about how much stress has built up in the fault, like the San Andreas fault. When is the next big earthquake? When it moves, it's going to move quite a bit. It's not like it moves a quarter inch and then needs the same amount of stress all over again. Once it's moving, it can move quite a ways to relieve all of that built-up stress. So in a rock, it's going to take a certain amount of shear stress before you'll get movement along a fracture, before the rock will actually shear. And oddly enough, and you'll kind of prove this in lab, or at least a little bit, the type of rock is not important. it takes about the same no matter which kind of rock you have. So what this means is that the amount of shear stress for any given normal stress is going to be fairly constant. This is actually a good thing for the engineers that go out and work on things because you don't have to have tons and tons of different values at your fingertips. The ratio is called the friction coefficient, and that's what you're going to use in the lab instead of that tangent of theta, since you don't have theta yet. So how does frictional sliding connect with the tensional fracturing? The stresses and angles involved in a fracture determine if a new fracture is going to form through tensional cracking or whether it'll just slide on an old existing crack. And the angle of those stresses is a big factor in this. Sometimes it's going to create a new crack because the existing fracture is too flat. Extreme example, totally perpendicular. If I'm pushing down on this, it's not going to slide sideways on the desk. It's not even logical. If I'm pushing at a little bit of an angle, it's still probably not going to slide. If I pushed hard enough, I would actually break it instead. On the other hand, the one that's not intuitive is if the angle is too close to the fracture plane, it's not going to move. Now, the reason, you think, oh, if I push exactly sideways on this thing, it'll slide nice and easily. That's true. That's a point source. We don't have point sources of stress in geology. They're big. If this is sitting here and I just try to walk up and push it like this, the whole thing either moves or doesn't move. If I put my palm on my hand and use the whole thing, and something's sitting here, it's not going to shear. It's just, nothing really happens. You have to have some angle so that the force is on one fault block and not really on the other fault block, or opposite direction on the other fault block. Pore pressure is the last big factor that comes into play here. Overpressure happens when there's more pressure inside the pore than what's outside of the rock. That pressure inside the pore pushing outward has almost the exact same effect as tension on the outside of the rock. So if you're filling up and pressurizing the inside, it's trying to split apart. If you're grabbing the outside and pulling, it's trying to split apart. And overpressure specifically is what they use for fracking, for example. Pump the water down, pressurize it, it creates cracks. So that's very easy to see proof that pore pressure enhances cracking. It can also just simply weaken the mineral by affecting the atomic bonds. Since water is a polar molecule, it can do this to some minerals and not others, and enhance cracking that way. We saw how it can affect sliding as well. We had a whole lab dedicated to the beer can experiment. Same idea, pore pressure, creating an easier sliding, or a lower angle for sliding the can down, i.e. less shear force required for it to slide. In a Moore circle, what this means is your circle is just going to slide to the left. The left-hand side of that failure envelope is always lower than the right-hand side. It's got a positive slope. So if you take your circle and you slide it left, you're moving closer and closer to that failure envelope. Eventually, if you have enough pore pressure, you hit it and the rock breaks. That's what, when they're trying to figure out, hey, how much pressure do we need to crack our formation, but not too much? It's that kind of a calculation. How far do we need to slide our Mohr circle? I'm sure they have computers to do it, and they're not doing it by hand, but the same concept. One important thing, though, with the pore pressure, the circle stays the same size. Your sigma 1 and your sigma 3 aren't changing because you have water inside your pore. So those are staying as fixed values. The difference between them stays fixed. The pore pressure is just making the effective change. And pressure is equal in all directions for fluid pressure. So that's why the circle stays the same size. So fluid pore pressure can enhance tensile cracking and enhance shear failure. So fluid in the rock is a really, really big deal if you're worrying about like slope stability and stuff. If the ground gets saturated, it drastically affects your slope stability equations. If you're worrying about rock stability in a mine, if there's a temperature change, that changes your pore pressure, and you can have blowouts in your mine. So just, I know you guys reviewed this last week for the stress circles, but you'll set up your x and y axis. Sigma n, your normal stress, is your x-axis, and sigma s is your y-axis. Whatever measured or given values you have for primary stresses, you take sigma 1 and sigma 3 and plot them on your x-axis. So you'll have 2 points. Find the center between them and draw a circle that has that diameter to include your sigma 1 and sigma 3. And you have your Mohr circle. It tells you exactly what the conditions are in your rock. If you plot your Coulomb failure envelope, you know how safe your rock is, so to speak. If it's really close to the failure envelope, you know it won't take much pore pressure or change in stresses to break it. If it's very far away, you know your conditions are very safe. As I had said before, in the real world, you'll never be able to measure it if it's on the circle. But it can be really close. And this gives you an idea of how much pore pressure you need if you want to break the rock. You could actually calculate it. Also, confining pressure. That's your sigma 3. It's your weaker of the stresses, but if you change sigma 3, it's going to change your circle dramatically. This is why bracing mine shafts and adding toe support to road cuts and so forth can stop rock failure. So the question is, why? Why does that confining pressure make that much difference? Well, if you have a Mohr circle here with no confining pressure whatsoever, basically atmospheric pressure. But since these are in megapascals, atmospheric pressure is effectively 0 on here. If sigma 1 is 8 megapascals, you have a circle like this, nice and big. It's hitting the Coulomb failure envelope. If we add some confining pressure, say 4 megapascals of confining pressure, sigma 1 is still the same, 8 megapascals. So we have the exact same sigma 1. The circle is tiny, nowhere near the failure envelope. The rock is completely safe because of that confining pressure that was added. So in the lab today, you'll draw some more circles. You'll look at the effect, what the size of the circle means, how it moves, where the rock is safe, where it's not safe, and how you can use the Mohr circle